Hi everyone. Today I'm going to talk about of the p-adic function of Bianchi modular form. This poster has two objectives. The first is to obtain the functional equation of the p-adic function of cuspidal Bianchi modular form of a small slope and sigma smooth cuspidal Bianchi modular form of critical slope that arise from classic modular forms. As the second objective is to construct the p-adic function of a small slope A-system Bianchi series. And this is a work in progress. Now I have to introduce some notations. Let K be an imaginary quadratic field of class number 1. Uh, all the results present in this poster holds for higher class number, but to facilitate the presentation, I will take class number 1. Also consider this quotient that is equal to the hyperbolic tree space defined as the complex number times the positive real numbers. We have two algebraic irreducible representations. The first one is this depending of integers k and l, and the second is this that is an irreducible representation of the special unitary group of degree 2. A Bianchi modular form of weight KL and level gamma is a map of representation F from the hyperbolic tree space to the tensor product of the two irreducible representations introduced above. Such map satisfies an automorphic condition for gamma, a harmonicity condition, and a growth condition at the cusp. That is the boundary of the hyperbolic tree space. We write MKL of gamma for the space of such forms. Some remarks about Bianchi modular forms. MKL of gamma is a finite-dimensional complex vector space. There exists Hecke action indexed by non-zero ideals. If S is an eigenform, we denote by lambda I the eigenvalue of Ti. There exists Fourier-Whittaker expansion, and the coefficients are explicitly related to the Hecke eigenvalues for a Bianchi eigenform. Also, we can define cusp forms via vanishing of constant Fourier coefficient, write SKL of gamma for the space of cusp forms, and such a space is equal to 0 when K is different to L. All non-zero cuspidal forms have parallel weight. Now, the p-adic function of a Bianchi modular form is naturally a local analytic function on the space of continuous homomorphisms from the Ray class group of K of level P infinity to the multiplicative group of p-adic complex numbers. Now, we are going to talk about the functional equation of the p-adic function in the cuspidal case. That is our first objective. We have this definition. If F is an eigenform of weight kk and eigenvalues lambda p, we say F has a small slope if the p-adic valuation of lambda p satisfies this condition for all p. And we say F has critical slope if it has no small slope. Now, consider F a cuspidal Bianchi eigenform of this level with n generated by nu that is prime to P. Then if F satisfies A, has a small slope, and is a successively p-stabilization for Hp of a new form, then the p-adic function that we are going to denote in this way was constructed by Williams. On the other hand, if F has critical slope, is the best change to K of a decent modular form, is nu away of P regular and sigma smooth, then this p-adic L-function of F was constructed by Barrera and Williams using p-adic families. It's important to say that these conditions are conjecturally, these conditions conjecturally always hold. The theorem obtained is that for F as above, for all kappa p-adic character, we have the following functional equation, where this is the eigenvalue of the freak involution. This ideal depends on nu, that is the generator of the level, and P. And this character depends on P and the weight of the modular form, of the Bianchi modular form. For the proof, there are two steps. The first one is to obtain the functional equation for F as in A, and then we put some functional equation in p-adic families and specialize it at F as in B, obtaining the result in the case B. For the first step, we have to put three ingredients together to obtain some functional equation. The first one is the main theorem in Williams, that is the construction and interpolation of the p-adic function when F has a small slope and is as in A. The second is the functional equation of the classical L function of F. And the third is the work done by Loeffler that uniquely determines the p-adic function of F when has a small slope by its values on the p-adic characters coming from a Hecke character of conductor dividing P infinity and has infinity type QR satisfying this condition. Then the second step, we take F as in B, also take a suitable neighborhood B of F contained in the base change to K of the eigencurve of Coleman-Maser, and using the functional equation obtained above, we have this new functional equation on families for all Y in B and all p-adic character kappa, where LP is a three-variable p-adic function constructed by Barrera-Williams, and the main property is that such function interpolates the p-adic function constructed by Williams for F of a small slope that is a base change to K. Omega is the Teichmüller character at P, and this is defined as usual for the p-adic setting. Finally, specializing the functional equation obtained for families in the point of B corresponding to F, we obtain the functional equation for F as in B. This is my first result and is available on arXiv. Now I want to talk about the A16 Bianchi case that is in work in progress. And it's basically generalize the ideas of secuspidality and partial modular symbols due to Velej and Dasgupta to the Bianchi setting to obtain, to construct the p-adic function of a secuspidal eigenform of a small slope. First, some definitions. Let's see this subset of cusps. We say that F is secuspidal if satisfies if vanished in all the cusps in C. Also, we have partial Bianchi modular symbols over C that are defined as the gamma equivariant homomorphism from degree zero divisors in C to this dual space from this polynomial space for L p-adic field. We have overconvergent partial Bianchi modular symbols over C that are the same as above, but the space is a p-adic distribution space. We have the definition of being a small slope of or critical slope, that is a generalization of the previous one in the cuspidal case, but adapted to weight KL. We have a control theorem, a partial control theorem, that gives us this isomorphism when the p-adic valuation of the eigenvalue of P, of the UP operator, satisfies these properties. Then we construct the p-adic function of a secuspidal eigen from F of a small slope as follows. First, we associate to F an eigensymbol in a Hecke equivariant way. Then we lift such eigensymbol to his unique corresponding overconvergent symbol. And finally, we define the p-adic function as the overconvergent eigensymbol evaluated in these zero divisors. Restricted to this space. Then a special situation is the following. Consider the base change to K of the theta series of a Hecke character C. Then, after P stabilize to have a small slope and turn this form into secuspidal, we obtain its p-adic function by our methods. Then we aim for a relation between such p-adic function with the Katz p-adic function of C introduced by Katz. We have some questions that are the following. How to turn a system Bianchi series into secuspidal? Or there exists explicit example of a system Bianchi series?